Okay, we're going to continue on in the looking at the functional group of ethers, and we're going to review one more synthesis of ethers. In the last lecture video, we talked about making epoxides and a new synthesis of the Williamson ether synthesis. And in terms of review, we can also synthesize ethers by using oxymercuration-demercuration. I should probably take a step back here and also say that if we wanted to react a double bond to form an ether, one of the things we could do is react this with H plus and an alcohol. Now remember that when we reacted the alkene with H plus and H2O, that we basically made, well, what did we add to the double bond? An H and an OH. How did we add it? Markovnikov. How did we add it? We added it 50-50 cis-trans. And so in this case, we would add the H to this carbon, the OH to that carbon. There's no chiral center, so there's no need to show the cis and trans 50-50. So again, there's not much difference between HOH reacting and ROH reacting. So in this case, what would happen? We would take our double bond and we would add H plus to it. Which carbon would we add to? The carbon with the most hydrogens. So we would add the hydrogen there, forming this carbocation at the most substituted position because that's the most stable position. And then what would happen? Then our alcohol would come in and add to that carbocation to then produce the oxonium ion, now with an alkyl group attached. And then what would happen then are another equivalent of alcohol would come in, catch this hydrogen as the pair of electrons goes back to form, as we lose H plus, to form then our final product, which in this case would be the ether. So we in essence added H and OR across the double bond. So that's a way to make an ether, by basically adding acid and alcohol to a double bond. Now, mercuration-demercuration was when we added mercury acetate to our double bond, and what that did was that added a mercury 1 plus to the double bond, so that we ended up with something that looked like this. We ended up with the mercury being partially bonded to both of these carbons, with each of them having delta positive charges, and then one acetate as the other acetate got kicked off. So if I really wanted to write this mechanism properly, I would have the two acetates like that, the pair of electrons going to the mercury, kicking off the other acetate. And if you're saying, oh, I forget what an acetate is, this is an acetate. That's acetate. So in this case, it would be a deprotonated acetic acid. So we form this mercurium ion, which looks strangely like a bromonium ion. But now, normally we would add mercury acetate and water. What if I added mercury acetate and an alcohol? What would happen? Well, the alcohol would add to the most substituted carbon, and then the mercury would end up swinging over. And remember, this addition would be 100% trans. So that we would end up with if the mercury, let's say, added from underneath, the mercury or the alcohol, sorry, added from underneath, we would end up with this oxonium ion below the plane of the ring. The methyl group would then be above the plane of the ring, as would the mercury acetate would also be above the plane of the ring. So this is Markovnikov addition, meaning that the alcohol adds to the carbon with the most substituents, most substituted, and then the mercury would end up like this, and then again another alcohol molecule would come in and it would deprotonate that hydrogen, or catch that hydrogen as this pair of electrons goes to form the oxygen to restore the zero charge on the oxygen. The H plus gets caught by the alcohol, so that we would end up with this is my final product, along with then H, the ROH2, so in other words, the oxonium ion of the alcohol. You could also, if you wanted to, you could also very easily say that the acetate could catch this hydrogen. Actually, that's probably what would happen. If the alcohol caught it, the oxonium ion would react with the acetate, so that we would end up with, most likely, in this case, that would be deprotonated by the acetate would deprotonate the oxonium ion of the alcohol, so we would end up with the carboxylic acid and the alcohol. So that's most likely the group that would actually catch the hydrogen. But either way, the hydrogen gets caught by something. So then this is my final product, which I'll go ahead and write up here. So after it's done, I've added my OR group, and my mercury now is now, they added 100% trans, but Markovnikov. So remember then, in the final step of this, we add sodium borohydride to this reaction. It replaces the mercury in exactly the same position with a hydrogen, so that in the end of this reaction, what I ended up doing was I ended up adding the hydrogen and the OR group, Markovnikov, 100% trans. Now, this is a bad molecule to use simply because there's another hydrogen there, but the hydrogen that I added was opposite the OR group. So oxymercuration-demercuration is just when you replace mercury and water with mercury and alcohol. And it's analogous to replacing H plus H2O with H plus alcohol. So these are other methods that we can use to make ethers that we talked about last semester with the reactions of alkenes. Okay. Now, there are times when we don't want alcohols to react, and we use what are called protecting groups for those. So let me give you an example here. Let's say I had this molecule and maybe I put an aldehyde over here. And so what I would like to do is I would like to take this alcohol and I would like to convert it to this carboxylic acid. But keep the alcohol intact. How could I do that? How could I do that reaction? Well, you'd say, I need to use an oxidizer, right? But remember that the oxidizer that I would use, all those strong oxidizers will also oxidize the alcohol to a ketone. So any oxidizer that I use is going to give me the carboxylic acid, but it's also going to give me the ketone. So this is where in organic synthesis, there's a term called protection. So what I'd like to do is I'd like to convert this alcohol into something else that won't oxidize and then somehow get it back. And the molecules that are actually shown in this chapter are to react the alcohol with a Silyl group, with a Silyl chloride. So this is called trimethyl Silyl chloride. And what will happen is that trimethyl Silyl chloride will react with the alcohol very much like the tosyl chloride that we saw before, and you're going to lose HCl in this process. So what you're going to end up doing is you're going to end up converting the OH group into an O with now this trimethyl Silyl group attached to the oxygen. And you would end up also making HCl. A silicon-oxygen bond is pretty strong, so that's a driving force for this reaction. Now, once you convert this, this is called a Silyl ether. And so once you protect that alcohol as a Silyl ether, it no longer is an alcohol. So I could then take this Silyl ether and say, you know what? Let's go ahead and react this with KMnO4. And when I reacted it with KMnO4, I would end up forming the carboxylic acid, but the Silyl ether would be untouched. So I could oxidize my aldehyde without oxidizing my alcohol. That's great if I can get this Silyl ether back to an alcohol. And so how do I do that? Well, if a silicon-oxygen bond is strong, I need a stronger silicon something bond to break this up. That something is fluoride. So that when you react fluoride with a Silyl ether, the silicon-fluorine bond is really strong. It's much stronger than a silicon-oxygen bond. So if you want to remove this trimethyl Silyl group, you add fluoride. The fluoride, it might be just easier to say, you know what, I'm going to add potassium fluoride. Sometimes people use cesium fluoride as well. Sometimes people use ammonium fluoride. Any fluoride will work. So the idea is that it will come in. All of these, right, are aqueous solutions. You can't just add solids in. So these are all aqueous solutions. When they reacted with this, they would strip off the silicon group and convert this back to the alcohol. So this is what is called a Silyl ether protection of alcohols. And it would allow me to react something else in the molecule with a reagent that would react with the alcohol if it was allowed to. So what I do is I protect the alcohol, do my reaction, and then this step is technically what is called a deprotection step. So that then I would get back my alcohol product. So this is it's kind of an aside, but it is an introduction to the idea of using what are called protecting groups. Because the reality is, just as another aside, that the reactions that we've been doing with just a single functional group are not realistic. In synthetic chemistry, we're reacting molecules that have multiple functional groups, and we want to make sure that we're just transforming one without the other. And so that's where the protection comes into play. And this is the first of a couple of protection schemes that we'll see in these syntheses. So this is Silyl, using a Silyl group to protect an alcohol and forming a Silyl ether. Why is it in the ether chapter? Because we made a Silyl ether. That's the best I can figure. Okay, so new methods to synthesize ethers that are not going to be new methods, they're old methods. So let's say I had methanol and I reacted it with tertiary butyl chloride. What kind of reaction would that be? Well, if you said SN1, you would be correct. I've got a tertiary halide plus what kind of a nucleophile? Since it's a neutral nucleophile, it's a weak nucleophile. So a weak nucleophile plus a tertiary halide goes by SN1. Oh, and it also goes by E1 as well, but let's just focus on the SN1 here. So what would happen? The carbon-chlorine bond would break, and we would form a tertiary butyl carbocation plus Cl minus. And then what would happen? Our weak nucleophile, our methanol, would come in, add to that carbocation, forming our oxonium ion. And then this pair of electrons would go to reform the O that doesn't have a charge, and the Cl minus would come in and catch that. So that we would end up forming as our final product tert-Butyl methyl ether and HCl. Okay. So we've seen this reaction before of reacting an alcohol with a chloride, with an alkyl chloride. The limitation on this is is going to either have to be a secondary or tertiary alcohol because the mechanism is going to have to go SN1. The weak nucleophile cannot do SN2 on an alkyl halide. Now, we could change this mechanism, or we could change this molecule up and also change the mechanism by saying, could I react tertiary butyl alcohol and methanol and do the same reaction and make as our final product tertiary butyl methyl ether, and then eliminate water as the product? So could I do this reaction? And the answer is yes, I can do that reaction, but my problem right at the moment is these are both nucleophiles. And so I'm going to need to add an electrophile to this mixture. Let's just go ahead and add H+. Now, I don't want to use H plus Cl minus because I don't want to do SN reaction. I don't want to do an SN1 and have that nucleophile end up adding to the carbocation that I'm going to form. So how about I use H plus that's attached to sulfuric acid, but then you're going to say, but isn't that going to do elimination? Isn't that going to do dehydration? And yeah, it might, but let's do this. Let's apply no heat to this reaction. So let's not heat it and make it go elimination, dehydration. Let's just use sulfuric acid and no heat. Okay, what's going to happen? Well, I'm going to protonate the OH of the tert-Butyl group to then form what? My oxonium ion and my HSO4 minus. tertiary oxonium ion, what happens next? Carbon-oxygen bond breaks, pair of electrons goes to the oxygen to now form the tertiary carbocation and water. Great. Now what's going to happen? Well, now my methanol molecule is going to come in. It's going to add to that carbocation. It's my nucleophile now. To form the oxonium ion. And now what's going to happen? Pair of electrons, the OH bond is going to break. The pair of electrons is going to go to the oxygen. Well, what's going to catch the H plus as it falls away? The SO4 minus. So I'm going to basically form my tert-Butyl methyl ether, and now H2SO4 is regenerated. And I already produced water up there. So if we react two alcohols together, we can make an ether by using, in this case, how would we classify this mechanism? Would this be overall SN1, SN2? If you said overall this mechanism would be SN1, that's how I would classify it. I'm substituting this nucleophile for the OH, and I'm doing it with the carbocation intermediate, so I would say that's an SN1 reaction. So we can make ethers using two alcohols and sulfuric acid with no heat. Okay. Now, typically this will go through a carbocation intermediate, and so we will protonate the alcohol that will give us the oxonium ion that will lead to a carbocation intermediate. Is it possible to do this reaction in an SN2 mechanism? It is, but it will require some tricks. We talked about diethyl ether in the last lecture video. So diethyl ether, the way you make diethyl ether is to take 2 molecules of ethanol, take some sulfuric acid, and you'll form diethyl ether and eliminate water. Okay, and the acid is a catalyst, and the acid would come from something like, again, H2SO4, because I don't want to have a nucleophile that will basically substitute for the OH. Now the problem here is that these are primary alcohols, so how does this reaction work? Well, it basically works like we would do all of our reactions, with a twist. So I'm going to react this with HSO4, H2SO4, right? So I'm going to take my alcohol, protonate it, have this pair of electrons go to the oxygen, and I'm going to go ahead and write equilibrium arrows in here because this is all subject to an equilibrium. And so I'm going to form my oxonium ion, right? And then I'm going to end up with my HSO4 minus. Now, this water cannot leave because it would form a primary carbocation that is only allowed to be written in mass spectrometry in the lab course. So what's the nucleophile? Well, the nucleophile in this reaction is going to be another ethanol molecule that'll come in, attack that carbon, and then kick off the water. So that means this is going to require some heat. So that transition state then would look like this. We would have our carbon partially bonded to the leaving group, which is the water, partially bonded over here to the ethanol that's coming in, and then there'd be one two hydrogens, and then a CH3 group on a dashed wedge. The problem here is that in terms of forming the final product is going to have a CH3, CH2, the O with the H attached to it with the positive charge, attached then to the CH2 with the CH3, and I'll end up eliminating water. So in terms of this transition state then, what are the partial charges? The partial charges are going to be a delta plus on this carbon, or on that oxygen, and a delta plus on that oxygen, since this oxygen right here is going from +1 to 0, delta plus. This oxygen right here is going from 0 to +1. Not a great transition state with two delta positives. That's why we need to heat. And then once I formed this molecule, this oxonium ion, then the pair of electrons would go back to the oxygen, right, to form the oxygen with no charge. And my arrow's gotten a little bit out of control there, so let me erase it. And then what's going to catch that H plus? The water is going to catch that H plus, so that then I'm going to end up with my diethyl ether and my H3O plus, which is essentially the hydrogen sulfate. You could also have the hydrogen sulfate, the HSO4 or HSO4 minus, catching this H plus as well. So these are all unfortunately equilibrium steps, so that my ether could be protonated with acid, and then the water could come in and attack, and I could reverse this diethyl ether all the way back to ethanol, although that's not likely to happen. The way this reaction is done, though, industrially, is you heat it to the appropriate temperature where, as this reaction occurs, ether only boils at about 30-something degrees Celsius, whereas ethanol boils at about 78 or so degrees Celsius. Give me 10 degrees and I'm good on that. So what you do is you heat this reaction hot enough so that when the ether is produced, it vaporizes and you collect it. It basically distills off. And then you just keep feeding this system ethanol and keep taking away the diethyl ether, and you've got a perfect industrial system. The acid acts as a catalyst, and so it just stays there and keeps doing the reaction. So this is sort of how the industrial synthesis of diethyl ether works. I would classify this as an SN2 because it never went through a carbocation intermediate. So with ethers, you can react different alcohols with acids, and you might get either an SN2 mechanism if you had two primaries, or most likely if you had a secondary or tertiary, then you would have it undergo SN1. So the steps are the same, it just depends on the exact type of alcohol or alcohols that you're reacting. And so this is how we can synthesize ethers, by using alcohols and H+. The mechanism is going to depend on what type of alcohol you're reacting together. Okay, now that's, in terms of synthesizing ethers, that's about it. We have Williamson ether synthesis to make, in essence, primary, secondary types of ethers where both groups on either side of the oxygen are either primary or secondary. If we want to make a tertiary ether where the carbon on one side of the ether is a tertiary carbon, then these reactions, the SN1 reactions of either two alcohols or an alcohol and a halide, would be perfect for those. Both of those are SN1 mechanisms. So what about the reactions of ethers? Well, there's two unwanted, well, I don't know, not necessarily unwanted reactions, but two reactions that don't get us anywhere synthetically. First is that if we take an ether and we react it with oxygen gas and a flame or a spark, we end up with CO2 and water and a lot of energy and either an explosion or a lot of fire. So we can burn ethers. If they're added to gasoline as additives to get a cleaner fuel, great. We're still combusting them. If we're in lab using diethyl ether, don't combust them, because then you'll end up with a fire. So that's a hazard we have to take into account when we're planning an experiment. That is one reaction of an ether. The other reaction of an ether is to form peroxides. So I touched upon this in the first semester lab, the more recent labs where we have a full-blown safety lab, and the idea that ethers will form peroxides. Now, this is going to be a free radical reaction. So this will occur with oxygen gas with no flame or spark over a long period of time. So this is a very slow reaction of ether with oxygen. And what we have to realize is that the oxygen has a paramagnetic form. Its diamagnetic form is when it just has the double bond, but there's also this paramagnetic form. If you look on YouTube, you'll probably find a video of people pouring liquid oxygen through the poles of a magnet. You can see the oxygen, the liquefied oxygen is attracted to the poles. That means it's paramagnetic, which means it has unpaired electrons. So oxygen has this basically diradical form. And as we saw last semester when we did free radical halogenation, and we did earlier this semester when we looked at the reactions of, I guess it was last semester, we did the free radical halogenation, and then we did the anti-Markovnikov addition of HBr with peroxides. Those were both free radical reactions, so this is going to be our first free radical reaction of this semester. And here's what happens. What happens is that the carbon attached to the oxygen has a hydrogen on it. And that oxygen, in its paramagnetic form, will basically abstract the hydrogen. So we'll break this CH bond, we'll give the hydrogen its unpaired electron to pair up with the oxygen's unpaired electron. We'll give the carbon an unpaired electron. And now what I'm using, remember what I'm using here is I'm using the fish hook. A full-blown arrow represents 2 electrons. A fish hook, which I should probably make my fish hook a little bit more distinctive, that there's just one side of it, that represents 1 electron. So I'm going to break the CH bond. The H dot's going to pair up with the O dot, and then the carbon's going to get its unpaired electron. So what I'm going to end up making is I'm going to make a carbon radical. I'm going to end up then reacting one of the oxygens with a hydrogen. And then the other oxygen is still going to be in its radical form. And then what happens is these 2 radicals then couple together so that that oxygen donates its unpaired electron along with that carbon donating its unpaired electron to now give us this molecule, which is an organic peroxide. a true organic peroxide would have two alkyl groups on either side of the oxygen. This is an ether peroxide. The problem with peroxides is that I have now embedded an oxygen gas molecule into my overall molecule. And whenever you do that with heat or shock, you'll end up basically forming oxygen gas. And so organic peroxides like ether peroxides tend to be solids. And so if they're shocked or heated, then what will happen is they'll undergo a tremendous expansion of volume and basically explode. So the problem with diethyl ether is over time it will react with oxygen and form a peroxide. And so in the lab, we have to make sure that when we open a bottle of ether, we immediately date it. We, after a certain number of months, would dispose of it. If we're unsure about the ether, we should check it for peroxides. And if it has any peroxides, what we normally do is add an iron 2+ to it, which will kill the epoxide or peroxide, and it'll convert it into something harmless. Now, in the old days, what would happen is you would have glass bottles of ether. And if the ether came in contact with air, sometimes it would form the peroxides, and it might even form the peroxides within the area between the top, the bottle's glass and the cap, which means that if you turned the cap, you could detonate the epoxide or the peroxide, because it could, basically that's a shock. Or if you pick the bottle up, it could explode because the peroxides were being shocked. Or if you heated the ether, it could essentially explode because it had peroxides in it. And so ether peroxidation, forming these epoxides, is a big problem with old bottles of ether, which is why we shouldn't leave them lying around. And a lot of ether comes with inhibitors to this, or antioxidants that will stop the formation of the peroxides. When I was in graduate school, the guy across the hallway was rotor-vapping some ether, and the round bottom that he was rotary evaporating with actually exploded, and the piece of glass from the round bottom hit him right in the safety glasses and took a chip out of his real glass safety glasses. So what ultimately they found out was that the molecule, or that the ether, had peroxides in it, and when he heated it on the rotary evaporator, it exploded. So we have to be very careful when we generate, when we use ether, to make sure that there's no hydrogen peroxide in, or no peroxides formed, because those peroxides will basically have a gas molecule embedded within them. And so with heat or shock, they can basically become oxygen gas and explode. So that's why we have to test ether. We have to make sure that we put its the date when we open the bottles up on it. So we have to be very careful, as you learned in the safety lecture for lab. I've also seen people come in detonation suits and take bottles out to a truck to be detonated if it's a really old bottle. So one time a high school teacher called me and said they had a bottle of diisopropyl ether. And I said, okay, how old is it? And they said, it looks pretty old. And I said, then just walk carefully out of the room. Because if you have a secondary carbon, that means that you can form a secondary radical that is far more stable than the primary radical that we form with diethyl ether. And so diisopropyl ether is very good at forming radicals. And ultimately, what happened is that one of his colleagues went in and decided they would take the cap off of it and dispose of it. And I just said, "What, did anything happen?" And he's like, "No, it didn't explode or anything." But there's a running joke that when you are ever trying to deal with something that is potentially explosive, you should always pick it up with the hand that you don't write with, just in case you don't have that hand when you're done. So we just have to be careful that peroxides, that we test for them with ether. So that's one of the things that we have to make sure that we be very careful of when we deal with peroxides. But for the most part, these are the two bad reactions of peroxides. The fact that they slowly form ethers in the presence of oxygen, like this diisopropyl ether apparently didn't do too badly with, and also the flame, the idea of ethers catching fire. And so we just have to be careful whenever we use ethers in the laboratory. Okay, so the final reaction that actually it's difficult, but it can occur, is to cleave the ether. So let's take tert-Butyl methyl ether, and let's go ahead and react that with two equivalents of HCl. You'll see why we need two equivalents in a moment. So what's the products of this reaction? What are they going to be? Well, let's write the mechanism out to try and figure this reaction and what the products will be. So the first thing is, you're going to hear me say numerous times that whenever we have an oxygen species reacting with acid, the first step in the mechanism is protonate the oxygen. Now I'm going to say that over and over and over again. So in this case, we're going to protonate that oxygen with the H plus of HCl, and we're going to go ahead and form our oxonium ion. And once we form our oxonium ion, then we can think about having cleaving one of the CO bonds. I'm going to cleave the bond to form the most stable carbocation, which in this case is going to be to break that CO bond and give the pair of electrons to the oxygen, and to form then a tertiary carbocation, and then our methanol molecule. So in this case, this methanol is a leaving group the way that normally water would be a leaving group. And so in this case, the methanol is going to leaving us with a carbocation. And then once we form that carbocation, the chloride is going to come in and add. So we're going to form tertiary butyl chloride as our first cleavage product to form the tert-Butyl chloride. But now what we're going to do is now we're going to react the methanol with the second equivalent of HCl. And so again, in this case, the first step in the mechanism is going to be to add H plus to the methanol. Now you may say, why didn't you lose the tert-Butyl alcohol? Well, we can't do that because then we'd form a CH3 plus, which is very unstable. So the first step in the mechanism is usually to form the most stable carbocation and cleave that bond. So now we have methanol attached to the H plus. And so we're going to protonate. The next step is going to be protonate the methanol. And so let's go ahead and protonate the methanol and form the oxonium ion. Now, water cannot leave, because if it did, it would form a CH3 plus, which is unstable. So the chloride's going to come in and add to that carbon, and then the water is going to be the leaving group. This might require a little bit of heat. this mechanism is going to be SN2. So this is going to be the formation. This is going to be an SN2 reaction. And originally we did an SN1 reaction. So typically we do have the SN1 reaction first, followed by then either an SN1 or an SN2 reaction, depending upon what the specific molecules are, the groups that are attached to the oxygen. So here's we're writing our transition state, our standard SN2 transition state, with the chlorine coming in and kicking out the water. The chlorine will be delta minus, the oxygen of the oxonium ion will be delta plus, and so we'll end up forming methyl chloride along with H2O. So in this cleavage reaction then, what we end up forming is the alkyl halides from the two groups that are around the oxygen. We tend to form the SN1 mechanism first to form the carbocation, and then depending on what the other group is, we could have SN1 or SN2. In this case, it was a methyl group, so it had to be SN2. So this is an ether cleavage reaction, and it requires, again, 2 equivalents of HCl to convert both of the alkyl groups into acid chloride. So in this case, we get T-butyl chloride, methyl chloride, and water as our final products of this reaction. Okay. Okay, so now we're going to talk about, in chapter 19, the reactions of dienes. And a diene is just a molecule that has 2 carbon-carbon double bonds in it, hence the name diene. And so what we're going to do is talk about the difference between a conjugated diene and what's called an isolated diene. So the structure of an isolated diene is that the double bonds in the isolated diene turn out to be, there's 2 or more single bonds in between the double bonds. That makes an isolated diene. So if we have 2 or more single bonds between the double bonds, then that is an isolated diene. And what that means is those double bonds will react independently. A conjugated diene has a single carbon-carbon bond in between the dienes. So it alternates and goes double, single, double. That is what is called a conjugated system. And this is a conjugated diene. And that will react slightly differently than the isolated one. Isolated dienes are really boring because basically all the reactions that we did with double bonds back in the first semester, we can do with an isolated diene. So let's say I added 2 HCl's to an isolated diene. I would add HCl Markovnikov to the one alkene, and then add HCl Markovnikov to the other diene, to the other double bond. So dienes are boring. Conjugated dienes are not boring because they will give us a different product than we would normally get. So we're going to focus on conjugated dienes because isolated dienes, we know all of the reactions that we did back in the first semester. And if you just didn't have me for first semester, then you have access to the Canvas site where you can go and take a look at all of those different lectures in order to understand that. So it turns out that a conjugated diene is more stable than an isolated one. And here is some calculations that I did on the computer to show that this conjugated diene, which is the top one, is more stable than the isolated diene, which is on the bottom. So on the top molecule, there is a double bond there, and there's a double bond there. They're separated by one single bond. Down here, the double bond is here, and there's a double bond there, and that is separated by 2 single bonds. So the bottom one is isolated, while the top diene is conjugated. And when we do calculations, what we find is that the top conjugated diene, I allowed that to have an energy of 0. I set that as kind of my baseline. So that had an relative energy of 0 kilojoules per mole. And then the isolated diene was found to be 7.98 kilojoules per mole more unstable or higher energy than the conjugated system, which I basically said make that 0. So that means that the conjugated diene is more stable than the isolated one because it has a lower overall energy. And so one of the things we have to do when we compare molecules is we have to make sure that those two molecules have exactly the same molecular formula, which these do. So one is more stable, the conjugated system's more stable than the isolated one. And so the way that we can take a look at that is by looking at the difference in the positions of the. So this one was, so the isolated was 8 kilocalories or kilojoules per mole more unstable. So how do we rationalize that? Let's draw a reaction or an energy diagram where energy goes up. So remember, molecules that have a higher energy are less stable than molecules that have a lower overall energy. So molecules that have a higher energy are less stable, and the ones that have lower energy are more stable. And so in this case, I set the conjugated system to be 0, and the isolated system then ended up with positive 7.98 kilojoules per mole higher in energy. And so that means that the isolated system is less stable by 8 kilojoules per mole. Is 8 kilojoules per mole a lot? We'll talk about that actually at a case study in the lab later on. But clearly the more stable in this case is the conjugated system. So the way that we can actually determine this experimentally is by taking these molecules and either combusting them using a combustion reaction by adding oxygen, or we could also measure their stability by hydrogenating them using hydrogen gas and palladium. Now, if we do either one of these reactions, they are both exothermic, which means going from the reactants to the products is going to be lowering the energy. Well, it turns out that in the case of hydrogenation, they will form the same alkane, and in the combustion reaction, they will form the same numbers of carbon dioxide and water. And so that sets a baseline where both reactions form the same product. So the isolated system, if it is less stable than the conjugated one, would have a greater negative heat of combustion or greater negative heat of hydrogenation than the conjugated system. And so what we do is we use the reverse. Experimentally, we measure the exothermic reaction energies, and then what we find is that the one that has the more negative exothermic reaction is the one that is less stable than the one that has the lower exothermic heat of reaction, and that would then give us the ability to determine which one is more or less stable in this case. And that's experimentally how we do that. So why is that the case? Why is the isolated system less stable or the conjugated system more stable? Well, let's write the conjugated and the isolated systems out. Let's talk a little bit about bond lengths. So in particular, we want to look at the bond lengths of the isolated system in what that carbon-carbon bond length is versus in the conjugated system, what is its carbon-carbon bond length. So the first thing is a standard sort of average for a carbon-carbon single bond is 1.45 angstroms. That's just your run-of-the-mill alkane. And so that is an average value. And from those calculations, what I could do is calculate the bond lengths of the isolated system. And what I find there is that bond length is 1.509 angstroms from the calculation. So to be honest, the single bond shortens up a little bit when it's attached to a double bond in this isolated system. Now, a carbon-carbon double bond length is about 1.34 angstroms in length. So that calculation showed that the double bonds were like 1.32 angstrom, and I'm not going to quibble over 0.02 angstroms. Now, the interesting thing is when you determine the bond length computationally there, what you find is that bond length is 1.466 angstroms. And so it's considerably shorter than the single bond that was attached to the double bond in the isolated system. And you can see it's kind of in between a single bond 1.54 angstrom and a 1.34 of the double bond. It's closer to a single bond, but there is some shortening, considerable shortening of the bond there. And so we have to explain why that bond is actually shortened. And we're going to explain it using basically a partial overlap of that, of the pi system that makes up that conjugated system. Now, as an aside here, this was thought to be the case and computationally was determined to be the case, and what was proposed was a partial overlap that we will show you in a minute once I correct myself here. And the reason the narration seems kind of disjointed here is because the computer ate my original narration for half of this video, and so I'm watching the screen trying to do play-by-play, and I move the dot an awful lot, and that's kind of frustrating me a little bit. But back to the problem here. So that bond was thought to be shorter, and the computations showed that it should be shorter. I will just say that one of the interesting things to me is that the experimental evidence that bond is actually shorter came about from undergraduate research students that worked over in Oberlin with a professor there, Norm Craig, who a lot of us in the chemistry department here at John Carroll have worked with through the years. And he and his undergraduate research students collaborated with a group in Germany doing some high-resolution infrared spectrometry to actually show that bond was shorter than a normal single carbon-carbon single bond. And so if you're interested in undergraduate research, that's a perfect example of undergraduate research students being involved in a project that, maybe not a lot of people care about, but certainly they were able to show that indeed that bond is shorter than what you would expect. And they provided experimental evidence of that people had just assumed was the case for many, many, many years. It wasn't graduate students, it was undergraduate students collaborating with a group in Germany that had the ability to do very high resolution infrared spectroscopy. So why is that bond shorter on the computer and also in real life? Well, it's because that partial overlap of that single bond. Now, what do I mean by that? What I mean by that is, let's draw the orbital picture here. And in order to draw the orbital picture, I need to know that all those carbons are sp2 hybridized, which means they all have p orbitals, and all the p orbitals in that system are parallel. So there's the first pi bond, there's the second pi bond. And so the p orbitals that are in that single bond are actually parallel to each other, and there's a partial overlap of that p orbital, of those two p orbitals with the in the single bond. And what that does is it creates kind of a little bit of a partial double bond character that shortens up that bond. And so that's the reason why we have a shorter bond, is because the partial overlap of the p orbitals being parallel to each other in those two pi bonds. Okay, so we're going to talk more about the reactions of conjugated dienes in the next lecture video, including how they're a little bit different than the isolated systems because of those, because of the fact that we have two double bonds that are conjugated with each other. And so that's what we'll look at, and there's going to be a lot of new things in that, new types of resonance structures, kinetic and thermodynamic products that we're going to talk about. So this is kind of setting the stage for the next lecture video, where we will talk about the reactions of these conjugated systems. And so that's what we'll do.